Okay, everybody, salam alaikum. Yalla, haltan bashi, inshallah. We carry on with our sessions in material science. I believe we've been up to page 7 of your lecture number 2. And the title is, there are two types of solid solutions. Of course, I just reminded you that solution means you have at least two components. One is the solute and one is the solvent. That's a solution. So we have one in minor, which is the solute, and one in major, which is the solvent. And as we said before, solutions could be liquid state, or could be gases like air. It consists of nitrogen and oxygen, so it's a gas solution. And it could be solid solution. It means the solute and the solvent are both solids. In general, we're dividing the solid solutions into two types. The first type is called substitutional solid solution. Look at the word substitution. And the other one is interstitial solid solution. So we have two types of solid solutions. If you move to next page, again showing you what is solvent and what is solute. If you look at the box of the solute on your left, it says dissolved element or solute atoms, could be element, and the solvent is base element or host atom. So we have one is the base, and the other one is as additive, or we can look at it the other way as sort of impurities, but it is not considered as impurities, but it is something similar to impurities. And in this case, when we have two elements, one is major, the one which we call it base element, that's the solvent, and the other one with a little concentration or in a minor concentration is called the solute. Remember, both of them are solid case because we're talking about solid solutions. Again, if you go to the box of solute, it says element or compound present in minor concentration. Again, we're saying that minor concentration, يعني تراكيز قليلة, and the solvent element or compound present in a great amount. Last point with the solute can be either metallic or non-metallic. Remember, when we have a solid solution, as we said many times, solvent and solute, solvent is always metallic, and the solute could be metallic or non-metallic. Could be metallic or non-metallic, but the solvent is always metallic. Okay, before we go further, let us talk about or comparing مقارنة comparing properties of alloys يعني سبائك in Arabic, and pure metals والعناصر أو الفلزات النقية. يعني ما الفرق بين الفلز النقي والسبيكة؟ يعني alloys and pure metals. طبعا alloys find very wide application in the industry than pure metals. يعني في الصناعة يستخدم الالويز السبائك يعني أكثر من استعمال الميتال نفسه. Some important uses of pure metals are هنا كاتبين لك بعض الاستخدامات. يعني متى نستخدم pure metals؟ عندما نحتاج high electrical conductivity، يعني الكتلات الكهربائية العالية، و high ductility، وعندما نحتاج إلى corrosion resistance are required. طبعا now we still talking about alloys and metals in general. Many pure metals are too soft for many uses. يعني الميتالز تكون سهلة يعني الطريق والحركة يعني وتغييرها إلى شيت صفائح، تكون يعني بزيادة تسمى soft يعني رقيقة أو ناعمة. They can be made harder by adding another element to the pure metal. If you want to make that metal which is soft, make it a bit hard, stronger, so you can use it in many purposes, in many applications. So we can add another element. So in this case, we're making like a mixture of elements, and this type of mixture of elements, one major element and one minor element, a mixture, yes, but it has a special name. We call it alloy. We call it alloy in this case. So alloy, remember, it's a mixture of elements. One major is a metal, is an element, which is called the solvent, and the other one could be metal or non-metal, or sometimes even compounds. But remember, the major, the solvent, must be element, and that element is a metal. In this case, we call it alloy. Of course, this explains why an alloy often has more uses than the pure elements it's made from. So the main reason is because the alloys are harder, stronger than the metal. Here we have an example about an alloy. Everyone, I think, have an idea about steel. Steel is iron, Fe, hadid, and we add some other elements, different elements, in different concentration or different ppm, and different elements, as I said, or could be more than one element or only just one element. It depends on what purpose you're using for. So pure iron, for example, is very soft. We cannot use pure iron, for example, in buildings, structure, or for bridges, as example, because it's soft, and by the time it might get bended, and it causes trouble for us. So we need to make this soft iron. Of course, when I say soft, the word is relative. Doesn't mean very soft. You can't just bend it by your hand. But I mean, when we use it, it can be bended. So that's why we consider it soft. Adding a small amount of tungsten is a metal, an element, to iron makes tool steel, for example. tool يعني معدات يعني في العمل يعني tool أدوات. Which is harder than pure iron? Steels are examples of alloys. There are many types of steel. طبعا we don't want to go through steel. Steel is just, we want to know, is a metal, mainly metal, which is iron, with some additives of other elements. In general, there are three types. For example, mild steel or tool steel and stainless steel. Of course, there are so many types of steel, but this is not our concern in deep for time being. Look at this one. You have steel, mild steel. The elements are carbon and iron. We have Fe and C, iron and carbon. The properties for this type of steel is easy to bend and pull into wires. You can make it wires or cables. So that's called mild steel. We need stronger than that, harder than that. For example, for tool steel, we add tungsten, and the properties for this type of steel is hard, can be heated to high temperature, accepts high temperature. And the other one, stainless steel, if we add chromium as an element, we can get like hard, and it doesn't get rust, yani corroded easily. If you look again to the elements, look at the carbon and iron and mild steel. Carbon is an non-metal, and in the second one, for the tool steel and stainless steel, the tungsten and the chromiums are metals. So this example for some metal and non-metal additives to the steel, to the iron, to make steel. So the difference between the steel and iron is a pure element, steel is iron and some other elements added. At that time, we call it steel. The majority, for steel is iron, is Fe. So we can ask a question or make a title for why alloys are harder than elements. So we're going to explaining alloy hardness. In the solid state, a pure metal has a giant metallic structure, a big structure, so many atoms combined with each other by sort of bonding, which is called metallic bond. And don't confuse between metallic bond and other types of bonding, such as covalent bond and ionic bond. This type of bonds is different. It's not covalent, and it is not ionic, pure covalent. And I think we did this metallic bond before. So the atoms are arranged in layers, many layers, and when a force is applied, when you're forcing that metal by, for example, hammering, the layers may slide over each other. So the layers are easy to move over each other, and that's why they are soft. When the greater the force needed, the harder and stronger the metal. When you need more force, it means your metal is harder and stronger. In pure metal, the force needed to make the layers slide over each other is small. It's not that much of forces, and this explains why many pure metals are soft. Now, in an alloy, there are atoms of different sizes. Of course, remember, in a pure metal, all atoms having same size. They are not different in size. The moving of these atoms over each other in a pure metal is not difficult. It can be forced, and then they move over each other easily. So that's why pure metals are soft. But when it comes to the alloy, and you're adding another element, different type of element, it means you're adding different size of atom. It's like you're sticking one different size in between these atoms, making that movement of the layer a bit harder. If you look at the figure, this one, that's the pure element. That's the pure element. These ones are a pure element. They have the same size. We added few atoms of another element, different element. In this case, you're adding different sizes of atoms into these atoms of the element. So now you have two different sizes. This one and this one and this one, they are the solute, and these are the solvent. So you have a solvent and solute. Now you're making alloy. Now, because the size of this atom is different than the size of this atom, or this one, or this one, or this one, this layer disturbed, has changed, not uniform layers anymore. So the sliding or movement of these layers are a bit hard now. It's not easy. It needs higher or stronger forces. So this means that a greater force is required for the layers to slide over each other. The alloy is harder and stronger in this case than the pure metal. And now we designed a table for you just to show you some differences between metals and alloys. In metals, they are made up of only one element, just only one type of atoms. So that's element, that's metal. And in alloy, as we said before, is a mixture of metals or metal and non-metal. So it's either just metals or could be metals and non-metals. But remember, we don't have an alloy with a mixture of two non-metals. With metals, of course, the ductility is high. And with alloy, of course, the ductility will be lower. With metals, we have lack, يعني ضعف أو نقص of mechanical properties like tensile strength, and yield strength, and hardness. And as you engineer, I suppose you know what's the meaning of this. And although I, again, written it for you, just in case if you cannot remember them, what they mean exactly, as you see in the table, tensile strength is the resistance of a material to breaking under tension. That's tensile strength. And if you go to the next page, the yield strength is the stress at which a material begins to deform plastically. So when the material starting deformation, that's called yield strength. And the last one, hardness, resistance of material to deformation, penetration by means such as abrasion or drilling or impact or scratching. That's a hardness. You go to the other side for the alloy, you see they are superior. They have superior mechanical properties. They have a very good mechanical properties. And that's why we use them in tools. Or steel, if you remember, that we say today. With metals, we have lack of strength. And with alloy, we have high strength. And the melting point for metals are relatively low if it's compared with the alloy. With alloy, they have higher melting points. When you have a mixture of two metals, or one metal and another non-metal, we get higher melting point. That's the case with the alloy. Metals more malleable than alloys, and the alloy, of course, less malleable than pure metals. For malleable from our previous sessions, I wrote it for you again. Just to remind you, malleable means it can be hammered into sheets. الطرق ممكن يعني بالعربي يقولون قابلة للطرق. قابلة للطرق. الدكتايل قابلة للسحب. Just give you some example about metals like copper, zinc, like iron, you know them, and alloys like brass and steel and solder. These are alloys. Excuse me. So brass is 70% copper and 30% zinc. Is a mixture of two elements. As you see, the copper is the major one, and the zinc is the minor one. And this type is called substitutional alloy. We will explain this. And steel, if you remember, just today we said that, it's an iron mainly with, for example, copper, or for example, chromium or vanadium. So many metals can be added to Fe, to iron, to make different types of alloys. And as you see the examples, such as manganese, Mn, silicon, nickel, titanium, copper, chromium, and aluminum. Of course, the only one non-metal in this case is the silicon. We put any question for you and we answer it at the same time. What we're saying, pure metals have many useful properties, good properties, yes, but they are not widely used. The question is, what's the reason? Why? Why we're not using them widely, although they're having good properties? Of course, the answer is they are often too soft, because they are too soft and have a low resistance to corrosion. So that's why, yes, they have good properties, malleability, ductility, yes, but we cannot use them directly until we make them harder, stronger. So we make them as alloy, as we said today, by adding some other elements, make it harder and more useful, more useful. Again, we're saying why we make alloys. There are some reasons for why we use alloys instead of metals. We put just 4 reasons. It doesn't mean that's all of them, could be some more, but that I believe the most important ones to improve the strength and hardness of metals. As we said again today, strength and hardness can be improved, can be upgraded, make it better by adding some other elements to the main element, to the main metal, make it more strong and harder. Second, to improve the resistance of metals against corrosion or rusting. Yeah, and I believe you know what's the meaning of corrosion. Corrosion in general is the reaction with oxygen, the atmospheric oxygen, and that metal change to oxides like Fe with O, oxygen, makes iron oxides, which is called rust in this case with iron. The rust is a special name for corrosion of iron. Number 3, to improve the appearance of the metal. And the last one is to improve the melting point, make it higher melting point. As we said before, the melting point for alloys is greater than, higher than the melting point of the metal. Okay, now we have a question says the physical properties of alloys are different from those of elements they contain, we know that. Now says give 2 examples to illustrate the statement. يعني أعطينا مثالين لتوضيح ذلك. Alloys are usually designed to have properties that are more desirable. Look at the word more desirable. We're not saying the metals are not desired, but to make it better, to make it more useful, we change them to alloy that are more desirable than those of the elements they contain. Properties such as strength and corrosion resistance may be considerably greater for an alloy than those of the elements they contain. I think in general we explained all these. As a result, alloys are more widely used than pure metals because it has better specifications, better properties, better hardness, higher melting point, better resistance to corrosion. Thus, in general, some reasons. So, steel is stronger than iron, one of its main elements. That's one example. The other example, brass is more durable than copper, but more attractive than zinc. يعني إذا نترجم durable يعني متانة بالعربي، متانة متين أكثر. يعني can we say in English يعني if I say it in English يعني it's able to withstand wear or pressure or damage يعني hard wearing يعني مثل porcelain مثلا porcelain for example that's the meaning of durable يعني in Arabic متين متانة يعني. We have another question says explain why an alloy is less malleable than the pure metal. I think we explained this before, but I try to put them in the questions and answer, which I believe is a better way to understand. Again, I'm telling you what malleable can be beaten into thin sheets without breaking. That's the meaning of malleable. Try to remember these two words. They are important in metals, malleable and ductile. So why an alloy is less malleable than pure metals? Right. If we go down in your lecture, is pure metals are rarely used in manufacturing because they are too soft. This makes the alloy harder and less malleable and ductile than the pure metal. Remember, alloys are less malleable than metals, pure metals, and less ductile than the pure metal. And remember what we said about layers today. That means in alloys, the slipping of the layer over each other would be harder, would be more difficult. Adding smaller atoms, smaller sized atoms can also have a significant effect on the alloy structure. Let's just compare again between pure metal and alloy. Look at the pure metal on your left. See, we have only one type of atoms. And of course, they have just one size, the same size, all of them. And because they make in layer and because they have the same size, for any force applied on these layers will make them moving easily over each other. Of course, when I say easily, it's a relative word in this case. Not easy, but if we compare it with alloy, it's easier. So pure metals are soft and easily bent malleable يعني bent يعني يطوى تطوي يعني the bending because layers of atoms of the same size can slide over each other easily. This sliding movement of atoms is called slip. slip يعني يتزحلق. slipped over يعني فوق يعني. Alloys are strong and hard, not easily bent. Layers of atoms cannot slide over each other easily as foreign atoms. What I mean by foreign atoms, I mean the atoms added to the metal. I mean, in this case, this is a foreign atom, يعني الذرات الغريبة الأجنبية الدخيلة يعني الجديدة. Foreign atoms are of different sizes and disrupt the orderly arrangement. disrupt هنا يعني خلينا نقول يشوه أو يمزق أو يخرب the orderly arrangement of metal atoms. يعني of course, if you look at these, size are same, and this size for this foreign atom, يعني the solute, it has a different size. Of course, two different sizes in one structure make movement of these layers hard, very difficult. Okay, we now going to types of alloys and their composition. The alloys are made from various elements. to increase the tensile strength and hardness to improve the matter's performance. I think we said this more than one time, but we sometimes repeat the things to make sure the students are getting the information, let us say, in different ways, different language. Sometimes you put it as a question, sometimes we underline it. So the student needs to concentrate on these words, on these terminologies, because that's the main words, that's the main things in this subject. So remember, increase the tensile strength and hardness to improve the matter's performance. In general, there are two types of alloys in general. In general, could be there's some other types, but that's the main types. It's two. In general, it's two. This one is called the substitutional solid solution. You look at the word, it says substitutional. Substitutional تعويض. تعويض يعني you put something instead of something else. يعني in this case, if you look at this figure, we have silver, copper. The copper, for example, is substituted here instead of one silver. Probably we have originally the copper, all copper, but we take off, let us say, this copper from here, and we substitute it by silver. So that's why it's called substitutional solid solution. So the substitutional solid solutions are those in which the solute and solvent atoms are nearly the same size, and the solute atoms simply substitute for solvent atoms on the crystalline lattice. So it means the solute and solvent atoms are nearly same size. Of course, in this one, copper and silver, they are close to each other in their size. They're not much different. That's one of the reasons we call it substitutional solid solution. Okay. And the solute atoms simply substitute for solvent atoms on the crystalline lattice, crystalline structure. The main categories of alloys are bearing alloys, corrosion resistance types, stainless steel, superauthentic alloys, and corrosion resistance has resistance alloys. Look at this one, that's the solvent, and that's the solute. That's the solvent, and that's the solute. This is the solvent. We substituted some atoms of the solvent by a solute, and the size, more or less, they are close to each other. They are not much different. But of course, they don't have exactly the same size because you're using different atoms. Different atoms definitely means we have different sizes, but that difference is not that much, not that big. They are very close to each other. So that's why we call it substitutional. We take off some solvent particles, some solvent atoms, we substitute it by some other atoms. This one, example, we have copper and nickel. We have copper and nickel. We have the nickel is the solvent that I say, for example, and copper is the solute. Again, this one will be like that, layers. That's the solute, and that's the solvent. That's the solute, that's the solute, and that's the solvent. So two different structures, but both of them are substitutional. Okay, we have some rules about, it's called Hume Rothery rules for substitutional solutions, rules to describe how an element might dissolve in a metal. So what we're saying, stable composition in equilibrium thermodynamically, metals, such as nickel and copper, they are good examples. Ed and Sn, Ag and Au, Mo and W. Of course, you need to know these symbols, what they mean. W, tungsten, molybdenum, Au, gold, Ag, silver. The solute and solvent should be of a similar size. This is the first rule for substitutional solution. We're not saying same size, but we're saying similar size. It means they are close to each other. The difference is not that much, and it should be about less than 15% different in their size. That's one of the rules for substitutional alloys. Of course, the second point, what we're saying, the crystal structure must match. Yani, the structure of these two atoms, when they are exist as alloy, should be close to each other, matching each other. Matching يعني شلون يتوافق معه ويتطابق معه. The crystal structures for metals of both atoms be the same, and not they're having different structures. Both solute and solvent should have similar electronegativity. Electronegativity, if you don't know what's the meaning of electronegativity means one atom, if you have two atoms, one atom has more affinity, more willing to withdraw the electrons, the pair of electrons towards itself more than the other. And for example, if you have HCl, I'm not talking HCl as an alloy, just giving you example in chemistry about electronegativity. If we have hydrogen and chloride, chloride as ion and hydrogen as ion, they combine with each other, making a bond, sort of covalent bond. But that covalent would be polar because a chloride ion has more affinity to withdraw the electron pair between the hydrogen and chloride. So the chloride in this case will be slightly negative, and hydrogen slightly positive. So you have like a molecule, bipolar molecule. One side is partially negative, and the other side of the molecule is partially positive. Same as in water, you have one oxygen combined with two hydrogens. Oxygen is more electronegative than hydrogen. The oxygen side will be slightly negative, and hydrogen side will be slightly positive. In this case, we have a polar molecule. So that's the meaning in general of electronegativity. So if we come back again to the alloy, when you have two elements, the two elements should have similar or very close electronegativities. Number 4, the valence of the solvent and solute metals should be similar. The valence is like oxidation state, but it's different from the oxidation state. Oxidation state with a sign, positive or negative, and valence is just a numerical value without sign. For example, copper has a valency of 2. It means that copper can combine with 2 chlorides. Valency of ion Fe could be 2 or 3. It means it can, for example, combine Fe2 with 2 chlorides. and Fe3 with 3 chlorides. That's the valency. I don't want to go through valency more than this and electronegativity more than this, but just you need to know the electronegativity and the valency for the solute and solvent should be very close to each other, not that different. So the other type of alloys is called interstitial solutions, made up of solids, are basically the ones in which the atoms of the solute are much smaller. Concentrate on this word, in which the atoms of the solute are much smaller and fit within the space between the atoms solvents, which are already present in a crystalline structure. It's just like you inserting a small particles between some relatively bigger particles. I repeat, you're just inserting small particles between larger particles, which are the solvent, of course. In this case, we're not substituting element by another element with similar size as we seen with substitutional. In this case, is inserting. That's why they call it interstitial solutions. So I repeat it, in which the atoms of the solute are much smaller, and fit within the space. Look at the word space, يعني داخل الفراغات. And we have a space here, for example, we have a space here, for example, a space here, space here, space here, here, and here, and here. That's a space. We can insert small particle in this space. Like in this one again. This are the solute, and this one is the solvent. Of course, a good example is iron and carbon in steel. Right, interstitial solid solution usually have a limited composition range. Doesn't mean a limited composition range. You cannot add as much as you want. There's a limit for that. There's a limit for that. How much you can add. Make it interstitial. A limited composition range. And are considered of secondary importance, but there are a few instances worthy of special attention. Let's see this example. Carbon in iron, a maximum of 2.8% of carbon can dissolve interstitially in ion Fe. Look at this example. So your limit is 2.8% of carbon. 0.129 nanometer carbon radius, 0.07 nanometer. Notice that the Fe is the solvent and carbon is the solute. So that's the radius of Fe, and that's the radius of carbon. Look at the radius of the atom of carbon is much smaller than the radius of iron. Okay, the interstitial solution of carbon in iron constituents the basis of steel hardening, very small amount of hydrogen introduced during acid pickling and cleaning, plating, or welding operations causes a sharp decrease in ductility known as hydrogen embrittlement. Okay. Go to the rules, as we've seen with substitutional, we have rules with interstitial solution and describe how an element might dissolve in the metal. Stable composition in equilibrium. We have equilibrium, stable, thermodynamic should be stable, not change. The solubility limit of solute in solvent depends on various factors. To the word, we're saying solubility limit. It means how much you can add of that solute to the solvent to make interstitial alloy. These were stated by Hume, Rothery, and as follows. Critical structure factor or crystal structure, metals that have the same crystal structure have greater solubility. Relative atomic size factor, it's called size factor. Okay, I believe we stop here is better to carry on with this type in the next session. Oh, sorry, it's not that much. Let us finish it. Let's finish it. So relative atomic size factor, relative atomic size. So we're talking about the atom size. The solid solution will tend to form if the difference in size of solute and solvent is less than 15. Remember, with substitutional, again, we mentioned this percentage. So the solid solution will tend to form if the difference in size of solute and solvent is less than 15%. The difference is greater than 15%, formation of solid solution will be limited. If you go further than 15% in general, at that time it's not going to be interstitial, might be going to be like substitutional. For good solid solubility, the difference should be less than 8%. That's for good one, for the best one. Of course, lower percentage is better. I mean, in this case, 8% or less than 8% is giving a good solid solubility. Atomic radii, I mean the radius of the solute atom must be smaller than the atomic radius for the solvent. I think we mentioned this before. About chemical affinity factor or electronegativity. So formulation of solid solution is favored for metals that have less chemical affinity more. Then a compound is formed instead of a solid solution. Remember, you have, especially with metals and non-metals, if they have affinity to each other, to combine to make a bond like ionic bond or even covalent bond, in this case, we're not getting an alloy, we're getting a compound. Instead of getting alloy, we're getting compound. Alloy means you have two metals or metal and non-metal. They're not combined chemically. There is no chemical combination between them. They just exist as a mixture with each other. And the relative valency factor, metal that has a higher valency will dissolve only small amount of lower valency metal. Metal that has a higher valency, look at the word higher valency, will dissolve only small amount of a lower valency. Whereas the metal with a low valency will have good solubility for the higher valency metal. The solvent atom must have more than one valency, more like iron. It has 2 and 3. So when two different metals or alloys are placed in intimate contact, atoms will slowly begin to migrate across the interface. This diffusion, unlike species under the influence of a chemical gradient, is called chemical diffusion. Remember, when you have two metals together, it doesn't mean that particles for the solute will stick at the same place constant. There is some movement. For example, the reason is because of the different concentration between two places, two spaces. So sort of diffusion will happen. Sort of diffusion will happen. Okay, I believe we finished this lecture. It comes to the end, as you see. I'm hoping you can understand what I said, and you need to go through your sheets, your malzama, before you listening to the video, or if you listen already to the video, then go back again to your sheets and read it yourself again. And if you have any question, anything not clear for you, you can call me on my phone number 00964 750 591 0373. I repeat, 00964 750 591 0370. Of course, that on Viber or WhatsApp. Thank you very much for your listening. I'm sorry if something is not cleared for you, but still, as I said, you have a chance to contact me, to ask me, and we can discuss your issue. Thank you very much. Assalamu alaikum. Khwa Hafiz. Have a nice time. And we meet again, inshallah.